Hi guys, I'm Baldado from Libo 4. The topic to teach is the first law of thermodynamics. So let me explain to you what is the first law of thermodynamics. So let's go.
The first law of thermodynamics, also known as law of conservation of energy, states that energy can neither be created nor destroyed. Energy can only be transferred or changed from one form to another. For example, turning on a light would seem to produce energy. However, it is electrical energy that is converted. The first law of thermodynamics applies the conservation of energy principle to systems where heat transfer and doing work are the methods of transferring energy into and out of the system. The first law of thermodynamics states that the change in internal energy of a system. The first law of thermodynamics states that heat is form of energy and that thermodynamic processes are therefore subject to the principle of conservation of energy. This means that heat energy cannot be created or destroyed. It can, however, be transferred from one location to another and converted to and from the other forms of energy.
The first law of thermodynamics states that the heat is a form of energy, and thermodynamic processes are therefore subject to the principle of conservation of energy. This means that the heat energy cannot be created or destroyed. It can, however, be transferred from one location to another and converted to and from other forms of energy. A way of expressing the first law of thermodynamics is that any change in the internal of a system is given by the sum of the heat that flows across its boundaries and the work done on the system by surroundings. This law says that there are two kinds of processes, heat and work, that can lead to a change in the internal energy of a system. Since both heat and work can be measured and quantified, this is the same as the saying that any change in the energy of a system must result in a corresponding change in the energy of the surroundings outside the system. In other words, energy cannot be created or destroyed. If heat flows into a system or the surroundings do work on it, the internal energy increases and the sign Q and W are positive. Conversely, heat flows out of the system or work done by the system will be at the expense of the internal energy, and Q and W will therefore be negative.
The first law of thermodynamics is present in the following objects. First is heat engine. The most common practical application of the first law is the heat engine. Heat engines convert thermal energy into mechanical energy and vice versa. Most heat engines fall into the category of open systems. The basic principle of a heat engine exploits the relationship among heat, volume, and pressure of a working fluid. This fluid is typically a gas, but in some cases, it may undergo phase changes from gas to liquid and back to a gas during a cycle. Refrigerators, air conditioners, and heat pumps. Refrigerators and heat pumps are heat engines that convert mechanical energy to heat. Most of these fall into the category of closed systems. When a gas is compressed, its temperature increases. This hot gas can then transfer heat to its surrounding environment. Then, when the compressed gas is allowed to expand, its temperature becomes colder than it was before it was compressed because some of its heat energy was removed during the hot cycle. This cold gas can then absorb heat energy from its environment. This is the working principle behind an air conditioner. Air conditioners don't actually produce cold, they remove heat. The working fluid is transferred outdoors by a mechanical pump where it is heated by compression. Next, it transfers the heat to the outdoor environment, usually through an air-cooled heat exchanger. Then, it is brought back indoors when it is allowed to expand and so cool can absorb heat from the indoor air through another heat exchanger. A heat pump is simply an air conditioner run in reverse. The heat from the compressed working fluid is used to warm the building. It is then transferred outside where it expands and becomes cold, thereby allowing it to absorb heat from the outside air, which even in winter is usually warmer than the cold working fluid.
Let's have the light bulb as an example. Think about the forms that we can see in a light bulb bulb, and where this energy coming from, and where is it going?
Well, the most obvious form of energy that you see in a light bulb is the radiant energy. You see, the electromagnetic waves, the light being emitted from it, and that light is the radiant energy. And that radiant energy is due to the heat in the filament and the electrons go through it. It generates heat, so you have the thermal energy. But where does this radiant and thermal energy come from?
First law of thermodynamics tells us it's not just being created out of thin air, it must be converted or being transferred from some place. This thermal energy is due to the electrons moving through the filament. They are moving through the filament which has some resistance, and that generates heat. And as electrons move through that resistor, they generate heat. So you actually have the kinetic energy of the electrons. But where is that kinetic energy coming from?
Well, it's coming from the potential energy. Maybe the light bulb is plugged into some socket. The electric socket has an electrostatic potential between the two terminals. So when you make a connection, the electrons are able to move. There is an electrostatic potential from one point of the filament to the other, which is the direction that the electrons are going in. So the potential energy is converted into kinetic energy of the electrons, and that gets converted into thermal energy and radiant energy. But what happens if you unplug the light? What happens to all the energy? Is it still there?
Yes, it is still there. The thermal energy is going to continue to dissipate through the system. The air inside the light bulb that's going to heat up, but then it's going to heat up the glass of the light bulb. So the thermal energy is going to be transferred, and the radiant energy is going to move outward, and it would be converted into other forms of energy, most likely thermal energy. It is also probably going to heat up other things.
Taking a bath, consider a situation where a person takes a very long bath. Immediately and after filling up the bath, the water is very hot, as high as 123 Fahrenheit. A person will then turn off the water and submerge his or her body into it. Initially, the water feels comfortably warm because the water's temperature is higher than the person's body temperature. After some time, however, some heat from water will have transferred to the individual and the two temperatures will meet. After a bit more time has passed, because this is not a closed system, the bath will cool as heat is loose at the atmosphere. The person will cool as well, but not as much, since his or her internal hemostatic mechanism will help keep his or her temperature adequately elevated.
Example of thermochemistry in life: putting ice into a glass of water to common, such as burning fuel of a car. When one exercises, the body actually cools down due to sweating. That's since our body supplies warm essential to dissipate water.